Hello everyone and welcome to the part 4 of the SIPS tutorials. I'm going to start by moving myself to the side so you can fully appreciate Wolfgang Promper's Centaurus A. This image is a nice example of how size matters in astronomy. It only took 20 minutes in each of these Sloan's photometric filters to take this image, but it was taken using our premium C5 camera and 1.5 meter telescope on Mount Paranal. As always, if you want more details, look into the description below. In this tutorial, we will look at how SIPS handles images. But before we get to that, I would like to mention SIPS documentation. Everything that we will cover in this tutorial, you can also find here on our website, gxccd.com. You go to Downloads, Documentation, SIPS, and today we will cover SIPS images. So if you want to read on details about some of these topics, you can do it right here. What is more, this documentation is also pretty much always up to date with the current version of SIPS. Let's now dive straight into SIPS. The native image format of SIPS is FITS, which stands for Flexible Image Transport System. It is essentially a matrix of pixels and then a header. Some of its features and requirements might be a little bit obsolete, but the truth is that it works very well and it's widely spread across the astronomical community. In SIPS, we can take a look at the FITS header right here. We can make changes here directly and then apply and save the image. Even if FITS doesn't understand some of these keywords, it stores them for the benefit of other processing software. For setting up what is stored in the FITS that SIPS itself takes using a camera, we can go to Settings, and here New FITS Headers, and we can set what is written into the FITS header of new images. Now, the data itself can be typically either 8, 16 or 32-bit integers. Some FITS files even use float point numbers. The float point numbers are slightly easier to work with in the code, but they have the deficit of being slower in general. Therefore, SIPS only uses either 16 or 32-bit integer numbers. 16-bit integer gives us a range of values from 0 to 65,535. SIPS can handle float point FITS files, but upon loading it converts them into integers. Let me move the picture here so I'm not covering the information down below. On top of bit depth, you can see whether the picture is monochrome or colorful. You can see the size of the picture. You can see the span of values in the picture, so we can already see that some of the pixels are saturated. We can see the current stretch. I will touch upon it in a moment, and we can see zoom. Right now, the image is 5 times smaller. I can go all the way to 8 times smaller, and I can also zoom in typically up to 8 times. In this case, I can only zoom up to 7 times, and that's because there's an upper limit of pixels. The limit is 32,768, which might sound like a lot, but this image is 4,000 by 4,000, and if we multiply it by 8, we get 1 pixel over this limit. Therefore, SIPS calculates the maximal zoom, and in this case, for this camera, it sets it to maximum 7 times. When image is zoomed in, we can use our right mouse button to move it around, or we can hold Ctrl and use a mouse wheel to move up and down, or Shift and mouse wheel to move left and right. I forgot to mention that we can zoom using a mouse wheel normally, or we can use this slider up here. It is possibly worth noting here that the FITS format does not prescribe the coordinate system. By default, SIPS uses 0, 0 value in the bottom left corner. With a pixel pop-up on, we can easily see it like this. This choice of having 0 in bottom left corner is typical for some of the professional FITS editors, but it's also the default choice in math and sciences in general. On top of the coordinates, this pixel pop-up also shows us the current value. We can take a quick look at the image info, which shows us things like maximum, minimum, mean, standard deviation. And when we select the part of the image, it as you can see, modifies the minimum, maximum, mean and standard deviation just to the selection. We currently don't see much in the image. There are some stars in the image which are saturated at the value of 65,000, but if we move around here, the average value is around 600. We can also see it here at the histogram tool that the most of my pixels are clustered around here at the very bottom. In general, the human eye is not well equipped to distinguish between all the 65,000 shades of gray. So we can use this tool to set the upper and lower limit. I can drop this here to get the range only to about 10 bits. And now I'm starting to see where all my pixels are. I can grab this here and say everything below the value of 509, for example, is going to be black. And everything above value of 800 is going to be white. Between these two numbers, I'm going to assign a shade of gray linearly. And now we are finally starting to see the nebula popping out. The transition between these two values does not have to be linear. We can move it to be logarithmic or exponential. When the value is logarithmic, we get a slightly better image of the nebula. We don't have to do this manually. There are some preset types which use statistics to calculate the bounds. For example, we can select the nebula and auto stretch, and it gives us this. We can probably get a slightly better result ourselves. The transition also doesn't have to be from black and white through shades of gray. We can use this tool, define palettes, right here to modify it. By default, we have black and white. We can also have negative, where we go from white to black. However, if we use just black and white, we are not using a significant part of our retinas, which is made to see color. So we can shift to color images, for example, this Inferno, which is one of the newish, perceptually uniform color maps from Matplotlib, which colors are range from black to yellow through this deep purple and red and orange. I should stress out here that this has nothing to do with coloring the image itself, has nothing to do with how this looks in reality. It's just a tool how we can visualize the values of the pixels. There are some more color maps which can be potentially useful. For example, this saturation color map, which uses black and white, but everything to the left of this slider is marked green, and everything to the right of this slider is marked red. So we can easily see which stars are saturating, and we can also see which part of the background are set to be just black. Right now there are none, but if I move this little bit right here, we can see that big parts of the background are now cutted and set to black. We can also go and define our own palettes entirely. I can go back to black and white, but I can say everything from here is going to be between blue and green. Then I click interpolate colors and I get this bizarre color map. Right now I can't think of any good reason why to use this, but in case it's ever needed, it is right here. Now that was all just one image. We can add more to the workspace by either clicking open, adding another image, nebula, or we can double click anywhere in the workspace to add image like this. Of course, we can use the drag and drop and select even multiple images, drop them right here, and they are all open like that. We can move them, rearrange them as we want. We can minimize them, and we can also use the functionality of the view ribbon where we can set all the images to cascade. Note that the images that I minimized are excluded. I can tile them vertically, horizontally. And if I want to maximize them, I can either click this button right here, and it brings all images into the tabs. If I want to go back, I can click Images in tab right here. Alternatively, I can double click the image like this. Note that the images that were minimized are now part of my group as well. So when I go back, the minimized images are right here. When the images are in tabs, some of these functions are disabled because they no longer make sense. At this point, it might be worth noting something about image persistency. We don't have to necessarily save all the images as they are taken from the camera or as we are working with them. As long as the image is open in SIPS, it stays in memory. So this is particularly useful, for example, for intermediate post-processing images. We will cover this a little bit more in the next video where we talk about lists, but I will just briefly mention here that if I create a new image, and now if I try to close it, I get a warning if I want to save it. I can add this image into the list, and then I can close it, and the image still remains persistent in SIPS. Now if I want to work with it, next time I open SIPS, I of course need to save the image. Speaking about saving, SIPS by default saves images again into the FITS format. By default it uses FITS, but it can also save them as FIT or even FTS. FITS images are mostly used by the scientific community. If you want to export into something more common, SIPS can export images either into 8-bit. This covers PNG files, JPEGs, bitmaps, TIFFs, and GIF files. Alternatively, we can export all 16 bits into PNG or TIFF files. It is worth pointing out here that the manipulation with the histogram does nothing to the FITS file itself. All the values are still there, we are just changing how we visualize them on screen. But when we export image into the 8-bit format, only the current stretch is used. Finally, when we have images in the workspace like this, we can use this feature to find image, to quickly find the one we want and bring it to the front. So this was, for example, the first one where we played the most with the histogram. Let's go back to images in tabs. Now I have already used the show pixel pop-up, which use the pixel values, but it might be also interesting to show that SIPS can use the center cross, which might be, for example, useful when we adjust the equatorial mount. SIPS was never meant as an image editing tool. Still, there are some simple editing tasks we can do in SIPS. We can go into this ribbon, and first of all we can select one part and we can copy it with Ctrl+C, and then we can paste it with Ctrl+V. Now after we press Ctrl+V, we can move this selection and we need to hit Enter. This is not particularly useful in one image, but we can, for example, take one part that we are interested in, copy it, and then create a new image. When we have something in clipboard, SIPS automatically adjusts width and height to what is there. So we can create a new image, do Ctrl+V, confirm it by Enter, and we can, for example, store just this one cutout. We can also make a selection and use this fill and fill it with value of 5000. And now we can see this is white, and we have this white peak that appeared on our histogram. Those were some very simple edits which we might occasionally find useful. Finally, let's take a look at a few of the transportation. We can rotate the image. We can even rotate it by arbitrary degree. And then we can mirror it. We can go into settings and set up transformations for newly taken images here. The last part of the transform ribbon is the binning. This comes originally from the CCD sensors, where binning, or more precisely hardware binning, was used to literally pool different pixels together. We can also do software binning as a part of a post-processing. With this tool, we can combine pixels in X and in Y, so this binning 2 by 2 would decrease the final resolution 4 times. Now, there is one important thing to keep in mind, and that's how we do the software binning. Let's get to some more reasonable image and switch the palette to the saturation. Let's change the histogram to the full range. Now we can see that we have some of these parts of the brightest stars that are already saturated. The traditional way of binning is summing pixels together, but this can have a downside of bringing 4 pixels over the maximum range of a 16-bit FITS. We can solve this by summing to 32 bits, but this has a downside of doubling the size of our images. There is an important note: for scientific photometry applications, it is important to mark this to keep saturated pixels, so those pixels that include at least one saturated pixel are still excluded from photometry. If you don't care about saturated pixels too much, we can also sum and keep the result 16-bit. Alternatively, we can use averaging instead of summation. This has a potential downside. When we are binning files with very low background noise, we can get under 1-bit resolution and the linearity might suffer a little bit. But again, this is something that only matters for scientific photometry. So, long story short, for photometry application, we should sum either to 32 bits or even to 16 bits, always with keep saturated pixels. For astrophotography applications, we can keep this unchecked and use averaging. And that should be it about images in SIPS. As a reminder, if you want to read more about anything we touched upon in this tutorial, check our documentation at gxccd.com or send us a question either down in the comments or send us an email to info@gxccd.com. In the next video, we will take a look at lists and how can they be used in SIPS. So if you don't want to miss it, make sure to subscribe and enable notifications. Bye for now.